Hi, today we're going to be talking through Module 3, Lecture 2. So if you go to the Moodle resources, you can see all of these things here. This is the PowerPoint for it. As usual, right, we have our code, which I definitely encourage you to go through again at the end. The main thing you'll need to change is you'll need to change the folder location to wherever you have this file saved, which is my M3L1 data. So we'll, kind of look at this as headers. This data is, I have a first blood pressure, I have a second blood pressure, I have a treatment indicator, and I have a cancer stage. So this is a lot like, right, the example we talked about in last class, where we were looking at blood pressure changes over time and whether or not that's affected by aspirin use. So this is what that data would look like. And when we read it into R, we can mess around with it. So I don't think I've mentioned this before, but in R, if you read in a variable name like this with a space, R will automatically go in and add periods in between them. But that's okay. You can still index them with the $sign. All right, so let's walk through the lecture. So this is all about two sample and paired tests for continuous data. The last lecture is going to be about two sample and tests for categorical data. So again, maybe a researcher wants to know if aspirin increases blood flow after consistent use of cancer. Maybe XI is a person's blood pressure and YI is a person's second blood pressure. Then ZI, which is equal to YI minus XI, denotes the person's change in blood pressure over a month. So this data set also consists of, I just showed it to you, right? TI, which is a treatment indicator, could equal 1 if a person received aspirin, 0 otherwise, and also SI, which is their cancer stage here. So as an example, right here, we'll just kind of work through and actually use R code to do these t-tests. First thing we want to do is we want to change our working directory. So my working directory is this here. It's users HAP, desktop, work, LSU teaching, Bsph program, module 3. That is where my M3L1 data.csv file is saved. I'm going to read it in with this command here. I also don't think I've mentioned, so these double pound signs or just a pound sign at all, that invokes the comment sort of environment for R. And so if you actually run that line of code, nothing will happen to it. So you can add comments just, to say, hey, this is what I'm doing, yada, yada, yada. I definitely encourage you to do that, to try to put comments. And the reason I say that is maybe you're working with a team and they want to look at your code so you can kind of tell everybody what you're doing. For me, right, if you're turning in code to me, then I can know, what you're doing or what you're trying to do. And then also, if you write papers, if you've written a paper before, and if you intend on writing a paper, the way it works is you'll submit a paper for review and you might not hear back for another couple months. So it's good to have the comments for you for when you go back to it. So I'm going to look at my data, head my data. This is my patient ID, treatment. You can see the periods in between blood.pressure 1, blood.pressure 2, and cancer.stage. First thing I want to do is create a variable with the differences in blood pressure. But what are the names here first and what's going on? So the names of the data, I've got patient ID, treatment, blood pressure 1, blood pressure 2, and cancer stage. And you can also see that on the header. Maybe I want to just get some information. I'll take the summary of the first blood pressure. This is the minimum, the 5-number summary plus the mean, the first quantile, the median, the third quantile, and the maximum. And these are the summaries of the second blood pressure. So if I index these, I can create a new variable. Now, I'm going to explain kind of what I'm doing here. So BP diff, that doesn't exist right now. But what I'm doing here is if I use this command, if I say, hey, data name, whatever, equals something, then that's going to create a new variable in my data set. So whenever I do head, that name will show up. So I can create new variables on the fly and name them whatever I want. So that's what I'm going to do here. I'm creating a variable named BP diff. It's the second blood pressure minus the first blood pressure. And then I'm going to summarize these differences. So you can see here in this command, I'm actually indexing it now. So $ BP diff, that's indexing the BP diff column here. So you can see right on the header, now I actually have a new variable stacked onto the end. And maybe I want to get some information like a histogram. So I'm going to do hist, data BP diff. This is my histogram. My title is histogram BP changes. My X label is BP change. And then I have 50 for breaks. So what breaks does is it sort of specifies how many boxes do you want. If you don't provide it, I'm not exactly sure how it picks a default, but it picks some number. If you don't add something here, if you want a more fine histogram or you have smaller bins, you're going to have 50 breaks or more. And if you don't want as many bins, you might set that to be 10 or 20. I don't think there's like a right or wrong way to do it, but like me personally, I usually use breaks equals 30 or 50 just to get an idea of what this looks like, unless my data set's really small. So I've got a histogram of it, and maybe I want to do a paired t-test. So maybe I want to know, hey, does the blood pressure decrease? Okay, so mu would be the population mean of the differences in blood pressure changes. And maybe I want to test the null hypothesis is that this mean change in blood pressure is positive versus the alternative is it's negative. So if I reject the null in favor of the alternative, that's evidence that blood pressure decrease over time. The average blood pressure decreased over time. So I can do that with the t.test command. This is very similar to what we did in module 2. So t.test, I'm going to index the data, the BP diff here. I'm going to set my mu is equal to 0, which is going to be the hypothesized mean I want to test for. And my alternative here is going to be less. So I can see the data here. My p-value is smaller, is very small. So again, this is like, 2.2 is like 0.00000, 16 zeros, and then a 2. That's what that e to the negative 16 means. And so since that p-value is really small, that means I reject the null that the mean blood pressure change is positive in favor of concluding that the mean blood pressure change is negative, so that on average, patients actually lost blood pressure over time. I can also get a confidence interval from here. You can see here, confidence interval goes from negative infinity to negative 19.72. So that's saying, right, that's sort of saying that the mean blood pressure change, not only is it negative, but most likely it's bigger than 20. It's bigger than negative 20 here. And this is my sample estimate is the mean of X. You can see that at the bottom, it's negative 23.25. So the average blood pressure change, just the simple average, is 23.25. On the right side, I'm doing a two-sided test here. So two-sided, all I'm doing is changing alternative to two-sided. And here I get a 95% two-sided confidence interval from negative 27.4 to negative 19.03. So, that gives me kind of some information of where I think the real change in blood pressure lives. And my p-value is super negative, is super small, right? So again, I would reject the null that the mean change is equal to 0 in favor of it being not equal to 0, some other value. Paired t-tests, we assume that the ZIs are normally distributed. So that could be true or it could be false. If you have a large sample size, that's usually a pretty reasonable thing to do as long as your data is somewhat continuous. If it's binary, maybe not. But in this case, right, it is continuous data. But when your sample size is really small, it's generally better to use a paired Wilcoxon test. Or if you've got data that's like Likert scale or something weird like that. So a similar example, a paired Wilcoxon test, right? I want to test that the median here is bigger than or equal to 0 versus the median is less than 0. And so you can see here, on the left side, I'm using the wilcox.test function. I'm plugging in data BP diff, that's the blood pressure differences. My mean here, my mu, my median I'm testing is 0, and I'm saying alternative is less and confident equals true. Again, whenever I'm doing a Wilcox test, I have to provide confident equals true if I want it. I get a really, really tiny p-value here, and this p-value is smaller than 0.05. So I reject the null that the median blood pressure change is positive in favor of the alternative that it's actually a negative change. So the second blood pressure is lower than the first, on average, that median is. I also get a confidence interval here, a 95% confidence interval, going from negative infinity to negative 19. Again, a one-sided test has a confidence interval always. It's truncated either by negative infinity on one end for a smaller than confidence interval, or positive infinity on the other end for a one-sided greater than confidence interval. And here's a two-sided confidence interval on the right side. I end up getting a confidence interval, right, of negative 27 to negative 18. Again, what is this test on the right formally testing? It's formally testing H naught mu equals 0 versus H1 M not equal to 0. So recall two sample t-tests. How do we do this? Recall the example exploring blood pressure change in cancer patients who take a placebo or aspirin. So again, right here, Z1I to Z1N1, that's the sample blood pressure change in the placebo group. And then to N2 here, this is the blood pressure change in the aspirin group. Mu1 is the population mean blood pressure change in the placebo group, and Mu2 is the population mean blood pressure change in the aspirin group. The goal here is to test the null hypothesis that these two means, the mean blood pressure changes, are equal, versus alternative that they're not equal. So what do we assume about our data here? We assume that the data itself from each group come from a normal distribution with different means, mu1 and mu2, and different variances, sigma 1 and sigma 2. It also assumes that all the observations are independent. So the blood pressure of one patient doesn't influence the blood pressure of another change. There are two versions of this two sample test. One is a pooled two sample test, which assumes the two variances are equal. And the other one is a non-pooled two sample test, which assumes those variants are unequal. Generally, right, the non-pooled, I would say use that. The reason why is it's more robust. So if the variances aren't equal and you use the pooled test, you won't get as good of operating characteristics. The test won't work as well as using a non-pooled. So let's first look at the means in each group. Z1 bar and Z2 bar, those are the average blood pressure changes in placebo and aspirin groups. So here I've got the mean, this is the blood pressure diff, and I'm indexing this thing, right? We talked about how to index these by data treatment equals 0. So this is pulling out all the blood pressure differences for treatment equals 0, which is the placebo group, and then for treatment equals 1, which is the aspirin group. So I'm taking the mean of both of those. S1 squared and S2 squared, those are the sample variances of the placebo and the aspirin groups. So I can use VAR here to get that. VAR, and again, I'm indexing the blood pressure difference for only the treatments equal 0. Should point out, right, when I'm indexing these blood pressures, I have to say equals 0 because that turns it into a logical statement. If you say equals 0, it'll reset all your treatment indicators there to all be 0. So you want to use equals here to index that. N1 and N2, these are the sample sizes at the bottom, 64 and 38.6. So this is an unpooled two sample t-test. Mathematically, right, it's just the sample average Z1 minus the sample average Z2 over the square root of the sample variance for the first group over the sample size, plus the sample variance for the second group over the sample size. And this test statistic follows the t-distribution, which looks like a normal distribution with these degrees of freedom. It's the smaller of the two sample sizes minus 1. You may see X1 bar and X2 bar online. They're the same. The definitions just matter. You just have to define what they are. If I want to get a confidence interval for this, I can get a confidence interval for mu2 minus mu1, which is the difference in those means, via the difference in the sample averages, plus or minus. This is the critical value from a t-distribution with df degrees of freedom, and times this square root, which is on the bottom of your test statistic. So notice, right, the confidence interval looks similar to the hypothesis test. It's got this bottom part, it's got this top part. The pooled two sample t-test assumes that the two variances are equal, the two population variances. So this is how you get a pooled sample variance. And all this really does is basically just the variance of your whole sample, more or less. It's just about that. It's not exactly that. It would be -1 here, but it's more or less the variance of just all the data together. And the pooled variance, this is the test statistic. It's a little bit different. It's pretty similar, right? In the sense of this bottom here, if you took this and you just replace these S1 and S2 squared with SP, that would be exactly the same thing. So you can see that here, SP squared. This test statistic under the null has N1 plus N2 minus 2 degrees of freedom. So it has more degrees of freedom here, which generally means you're going to be more likely to reject the null. Okay, the t.test, again, this is a function that we used for paired t-test just now. We can actually do this using this x and y here. So I can plug in x, which would be one sample, and y, which would be another sample. I can also plug in a formula, which I'll show you how to do that as well. A formula based on T, which is our treatment indicator, and the blood pressures themselves. And then this var equal here is going to be either true. If it's true, I'm going to do a pooled t-test. And if it's false, I'm going to do a non-pooled t-test. So before I get into it, let's just look graphically what's going on. So this is the box plot of blood pressure change by treatment. How do I do that? This is the first time you'll see a formula. Notice how, right, I've got this kind of tilde up here. It says data BP diff tilde treatment. So in general, right, a formula looks like, for example, in R, Y, let's say I'm going to do X plus Z. When I plug this into any kind of function, it's going to assume that I want to do something with this formula, do some kind of modeling. So if I'm doing this with the t-test, right, you know, I might say like this, y given t. So that's the same thing here. So it's saying, hey, look, I've got this formula, this relationship between blood pressure difference and treatment, plotted in a box plot. I'm adding an X labeled treatment, I'm adding a Y labeled blood pressure change, and then I'm adding a title to it. So you can already kind of see, right, that there is a shift, a bigger, so more positive blood pressure change in the no treatment group. That would be placebo versus the aspirin group. You can see a shift here. If I do a t-test here, I can do it this way. This way I'm saying, hey, look, I want all the blood pressure differences, but I only want for treatment equals 0. Again, equals equals. Same thing for treatment equals 1. I'm plugging them in that, if you look on the slide before, in that X and Y spot. And then I'm saying var equals equal to false. I get a very, very small p-value, which is saying that the difference in means is not equal to 0. So I'm rejecting the null that the two means are equal, right? So I'm testing, again, I'm testing this here, this hypothesis. I'm rejecting the null because the p-value is small in favor of the alternative, that the means actually aren't equal here. The mean changes. And that's reflected, right, in the data being shifted. I also get a 95% confidence interval here. This 95% confidence interval is for the difference between the mean of X and the mean of Y. So 15 minus -36, that would be positive, you can see, right? And I get a confidence interval for this difference of 12.3 to 28. So because the Y value is a lot smaller. So the first sample, right, has a mean that's somewhere between 12 and 28 higher than the second sample, which is of patients that got aspirin. I can also use a pooled variance estimate here with var equals true. Here I get the same conclusion, right? My p-value is really small, and I think I get a slightly different confidence interval, you can see. This is my confidence interval for mu2 minus mu1, which again, right, that's the difference between the blood pressure difference for patients treated with aspirin versus placebo. That's the population mean difference. Okay, the default in t-test is unpooled. Why? Because pooled t-tests can have poor type 1 error or power when variances are not equal. So I think it's better to use unpooled just to be on the safe side, just as kind of a rule of thumb. Okay, I also might want to know, did the blood pressure change by a certain amount? So here I might want to test, hey, if I look at the difference in blood pressure from the aspirin group minus the placebo group, is that difference bigger than 10 points, something like that. So delta here is something I can put in versus it being greater than that. So delta equals 5 would mean those that take aspirin have a decrease in blood pressure more than 5 units over those that took placebo. So I can actually test this here. All I need to do is add mu into the t-test. So just like I was doing before, but now mu is the differences. It's not, I'm not testing, does the mean equal to this? I'm testing, is the difference, is the mean difference equal to this? And I can see, right, I get a really small p-value in terms of the greater than. So I can conclude that this difference is actually less than 5 here. Now, again, right, this is the difference of mean in group 0 minus mean in group 1. So it's bigger than 36 or bigger than 20, this difference. Similarly, right, I can do this with pooled variances using var equals true. That's all I'm doing on the bottom. And here is my confidence interval, right? Again, it's a one-sided confidence interval, so I have imp for one of these. I'm also doing this a little bit differently here. You can see, right, on this last slide, I'm plugging in X and Y. Here, I'm plugging in a formula, and this formula looks like the box plot. I'm saying the blood pressure different, tilde treatment. And it's much like that ZI TI notation. So it's this sort of, if I plug this kind of thing here into a t.test, R knows that I'm trying to basically split this out into 2 groups and do a 2-sample t-test. A Wilcoxon rank sum test. It's just like a 2-sample t-test is a version of a t-test. A Wilcoxon rank sum test is a 2-sample version of a Wilcoxon sign rank test. So all I'm doing here is, instead of testing means that are equal, I'm testing that the medians are equal. So again, M1 is the population BP change in the placebo group. M2 is in the aspirin group. The goal is to test that the 2 medians are equal versus they're not equal. And I can do this in 2 ways. One way is I just plug in all of my data from the first treatment group and the second treatment group. Again, I'm indexing here the blood pressure differences. I'm grabbing the zeros, I'm grabbing the ones. Or I can also use a formula, BP diff tilde data treatment. That's a formula. They both give you the same answer. I get a very, very small p-value. My alternative is that the median difference is not equal to 0. I reject the null that they are equal in favor of the alternative. So I can conclude that the median blood pressure changes between the 2 treatment groups are also not equal. And if I want to get a confidence interval for this difference, I do conf.int equals true. So that's it for today. Next lecture, we will go through categorical tests and also look into the homework.